Hello everyone, you are watching the Space Channel. String theory is the youngest scientific concept to have brought about fundamental changes in physics. It is remarkable in that it claims the title of a paradigm of all existence, yet at present it remains merely a set of equations jotted down in a rough draft. After all, string theory was not conceived until the 1960s. It has no single author, is still unfinished, and lacks experimental confirmation. So why do scientists treat such an unpolished scientific idea with such seriousness? The answer should be sought in the research of Albert Einstein. By devising the special theory of relativity, he initiated a revolution in physics and opened the way for quantum mechanics, which describes the behavior of elementary particles. Later, Einstein linked his theory with gravity, presenting the general theory of relativity. He explained gravity as a curvature in the fabric of space-time caused by massive bodies, a view superior to the one offered by Newtonian classical physics. Yet it left unanswered the key question: which elementary particle carries gravitational fields? Today, physicists have reached a consensus that there are four fundamental interactions: the weak, strong, electromagnetic, and gravitational interactions. The weak and strong interactions are associated with atomic nuclei, and their carriers are quarks. The carrier of the electromagnetic interaction is the photon, which at different frequencies gives rise to the entire radiation spectrum. The influence of gravitation on bodies with mass is well studied, but the mechanism of its origin is unknown. Scientists hypothesize the existence of a hypothetical particle, the graviton, as the carrier of gravity. However, this hypothesis has yet to be proven. Here we arrive at the point where using string theory allows us to lift the mysterious veil that hides physical mechanisms from us. The fact is that the particles responsible for the weak, strong, and electromagnetic interactions can today be described by quantum physics. This theoretical procedure is called quantization. After quantization, it becomes possible to predict the discovery of various particles and to conduct experiments to search for them. A key feature of quantization is that, although the smallest objects in the universe are described as probability clouds, the shape of those clouds approaches a sphere, which in turn is simplified to a point. Representing objects as points suffice to discover the elementary particles predicted by quantum physics that we know today. Yet in the case of the gravitational particle, the graviton, this approach did not work. Therefore, scientists asked what more complex generalizations of an object's shape than a point could be used in quantum calculations. To understand which representation suits this purpose, we need to perform a thought experiment. Take a laser pointer and shine it on a sheet of paper. If we stand behind the pointer and look at the paper at a right angle, we see a laser dot. But if we stand to the side, the laser, when observed, will look not like a dot, but like an elongated line, a string. Let us modify this experiment by adding the time dimension and enlarging the spatial scale. Turn the laser on for a few seconds and then turn it off immediately. If we look at the sheet of paper, we again see the laser dot, which appears quickly and disappears quickly. But if we look at the laser from the side from a very great distance, it will appear to us as a thin straw moving forward through space. The segment we observe has a beginning, which formed when the laser was switched on, and an end, which formed when the laser was switched off. What conclusions can we draw from this experiment? First, different phenomena in objects can appear completely different from different angles of observation, either as a single point or as a line string. Second, due to the speed of light limit, we can observe the beginning of a line of radiation without being able to instantly determine whether the object continues to exist at the same moment as we do, or whether it no longer exists. Only its past image reaches us in the form of a line of radiation. That is, an object can have an infinite number of reflections on different observational scales. At the same time, not all reflections are accessible to us due to physical constraints, such as the speed of light. Some characteristic of an object truly exists, but we will never be able to see it because it is present in the reflection that is inaccessible to us. String theory is a concept and a mathematical model in which elementary particles are represented not as point-like objects, but as linear, string-like objects curled up in multidimensional space. Physicists developed this theory to comprehend, through mathematical formulas, the vast reflections and dimensions of the universe when direct observation of these reflections, whether by eye or with scientific instruments, is impossible. It is precisely in invisible dimensions that the graviton, the carrier of gravity, may be hiding. However, in the attempts to achieve success in this search, scientists, with their hypotheses and calculations, fulfill the well-known saying, "The road to hell is paved with good intentions." The mathematical apparatus of string theory is a real hell. The theory does not work and does not yield correct calculations when applied in our usual three-dimensional space with a single line of time. For its viability, string theory requires application in an imagined 10-dimensional space. Yet even the results obtained in that space have so far not been converted by anyone into quantities compatible with the everyday world. From a philosophical standpoint, this problem arises from the following paradox. String theory enables us, through mathematical formulas, to perceive what is inaccessible to observation via light radiation. But at the same time, we have no understanding of what the result of an observation obtained in some other way, rather than by capturing photons, would look like. In other words, we have gained the ability to perceive a particular dimension, but we have never seen it before and have no idea what exactly we expect to see in that dimension. To demonstrate the practical realism of string theory, experiments were planned for the Large Hadron Collider. According to the scientists' design, elementary particles were to collide at high velocities with enormous energies. If gravitons, the carriers of gravitation, exist, then after the collision, they should break off from the particles as fragments and slip away into extra, indeterminate dimensions. This could have been confirmed by showing that the energy of the fragments after the collision was lower than the energy of the particles before impact. The missing energy would be those enigmatic gravitons themselves. Yet, as of 2025, no practical experiment has been conducted that either confirms or refutes this hypothesis. What practical uses might string theory have? A key direction is the study of the internal structure of elementary particles. For nearly its whole history, humanity has asked, how small is the indivisible particle out of which matter is made? Little more than 2 centuries ago, the atom was considered that particle, and its structure remained a mystery. Today, we know that the atom is only one level in matter's hierarchy, for atoms divide into protons, neutrons, and electrons, which in turn consist of quarks. It is entirely plausible, however, that quarks themselves can divide into still smaller constituent particles. A serious obstacle prevents us from finding out. As noted above, humanity's main way of investigating the universe is to analyze photons of electromagnetic radiation emitted by various objects. A photon is very tiny, but the putative components of quarks are even tinier. Consequently, photons cannot interact with them, and these smallest particles remain inaccessible to direct observation. Nevertheless, something has been glimpsed, and the picture proved unexpected. Under powerful electron microscopes, the elementary particles that make up atoms do not appear as solid bodies, but as loose clumps shot through with gaps. String theory explains such a structure by asserting that these particles are clumps of strings, twisted in a particular way and vibrating at a certain frequency. A simple everyday analogy is a thread wound into a ball. String theory further posits that the thin filaments of matter from which particles are wound can be infinitely fine, and that to describe their properties, one must employ not three-dimensional, but 10-dimensional space, as mentioned above. An additional ingredient is the vibration frequency of a string, which determines the particle's physical properties. Historically, string theory was invented to solve 2 practical tasks: to explain which particle is responsible for transmitting gravity and to link gravity with all other interactions, so as to create a theory of everything governed by a single force. Yet despite colossal efforts, it has not become a breakthrough on the scale of Einstein's relativity. 60 years after its first formulation, it has come to an impasse. Some scientists believe string theory is mistaken and misleading, so its development should cease, and attention should shift to other branches of physics. Others contend that a theory aspiring to describe everything cannot immediately deliver unique discoveries and results. This debate arose because, within string theory, most achievements have been theoretical and largely mathematical rather than physical. Attempts to confirm the theory experimentally at the Large Hadron Collider have so far led nowhere. There is speculation that they will not succeed in the near future because successful tests would require instruments possible only at a radically higher level of technological development, or existing instruments enlarged to colossal dimensions, the size of a star or even a galaxy. Nevertheless, some progress has been made in developing string theory, and 3 milestones stand out. The first event, the first superstring revolution, took place in 1984 when researchers developed the concept of a string that, depending on its configuration, forms the basis of elementary particles. It should be noted that string theory is the general label, whereas the more precise term is superstring theory. Moreover, it is not a single theory. There are 5 superstring theories, and their development accelerated after 1984. In 1994, the second superstring revolution occurred. American theoretical physicist Edward Witten proposed that the 5 existing superstring theories are components of a larger theory. He called it M-theory, known to popular science readers as brain theory. The letter M in M-theory carries no fixed meaning. Some scientists think it stands for matrix, others for mother theory. M-theory's chief distinction from earlier superstring theories is that it entails an additional 11th dimension, and by means of it, seeks to unite all superstring theories. In this model, the strings that form elementary particles are treated as flat ribbons, fantastically curled in multidimensional space. The final milestone was the discovery of the ADS-CFT correspondence in 1997 by Argentine-American physicist Juan Maldacena. Its main result was to propose a theoretical mechanism that allows calculations to be transferred from more highly dimensional spaces to spaces of fewer dimensions. In other words, it promises to interpret results obtained in 10 and 11-dimensional spaces, where string theory operates more quickly and easily within our familiar 3-dimensional world and the ordinary flow of time. Thus, string theory is an exceedingly ambitious framework on which the global scientific community has set its sights. Due to the lack of clear, practical results, debates persist over the theory's necessity and validity. Nevertheless, researchers do not relegate it to the background, for the emergence of new technologies, particularly artificial intelligence, may finally enable the breakthrough that will let string theory become a full-fledged scientific concept explaining the workings of our universe in every aspect.